Hello everyone. Okay, so in this session we will continue our lecture on the topic 2, okay, which is on the influence line method. So without further ado, let's we discuss in detail. Okay, so as an introduction, basically influence lines is about to analyze the moving load, where you can see in the brief, an influence lines indicates the effect of a unit load moving across a structure. Okay, one can tell at a glance where the moving load should be placed on the structure so that it creates the greatest influence at a specific point. Okay, so another things that I wanted to highlight in this slide is the last point. So this will obvious differentiate between the influence lines analysis with respect to the normal beam analysis. Okay, so in a normal beam analysis, you deal with a fixed load. Okay, so let's we look in detail on this point. The difference between influence line diagram and the shear or moment diagram is influence line represent the effect of a moving load only at a specific point, while shear or moment diagrams represent the effect of a fixed load at all points along the edges of the member. So in other words, what we can summarize from this sentence is by using the conventional or the usual method of a beam analysis, so you will get one's value of means that you will get one graph of bending moment shear force for one fixed position of load. Okay. Meanwhile, in the influence line diagram analysis, so you need to identify what is the critical position of a moment and the shear force value based on the moving load here. Okay, so it is very tedious if you wanted to carry out the usual way many times by positioning the load at along the beam. So this will be create the long step of calculation. So due to that, the influence line diagram come to simplify the usual method of a beam analysis. Okay, so let's we see on the background of this particular influence line diagram concept. Okay, so basically they have two method that they can analyze the influence line diagram in a beam. Okay, so they have the first one is a tablet values. The second one is an influence line equation. So I don't want to discuss in detail on the first method. So we will focus on the influence line equation. Okay, by using the equation, it's more flexible rather than by using the first method, which is using the table's value. Okay, so by using the influence line equation, you need to establish an equation. Okay, for instance, here this slide trying to shows how we can develop the influence line diagram. So I can short form that term for ILD. So right here we have a simply supported beam where one unit load is applied on the beam. So this one unit load is moved along the beam from point A to point B. So with a distance of x that measured from support A. Okay. So by looking on this diagram, actually you can develop the influence line diagram for the reaction support at A. Okay. So the first thing that you need to do is you need to figure out the equation of reaction at support A based on this particular free body diagram. So by taking moment at a point B, about a point B, so you can see that we have RA multiplied by the 10. Okay, and we have 1 multiplied by 10 minus x. Okay, so 10 minus x. So rearrange this equation, so you will get that one equation of RAY equal to 1 minus 0.1x. Okay, so by using this equation, actually you can develop a few points. Okay, for instance, here let's consider x in equal to 2.5 interval. So start with x equal to 0. So by using this equation, you will get that RAY equal to 1. And for the subsequent value of x, which is equal to 2.5, 5, and at the end is 10 meter. So you will get the corresponding value of RAY. And by using this value in the table, so you can plot the graph for the ILD for support A, okay, direction support A. So and you can simply to use this particular diagram to indicate the critical point of I mean the critical value of based on the positions of one unit load along the beam. For instance, if I wanted to get the value of reaction support at A when my load is positioned at 5 meter, okay, in the beam, at the midspan and the beam. So okay, I can simply to get the value of reactions at support A by using this graph. So by offset the value of a position of a 1 unit load here, so I can get the value of a reaction at support A by looking on the vertical axis. So meaning that this graph is about the reaction support A against the distance x, okay, which is referred to the span of a beam. Okay, so let's discuss in detail on this method by using the example 1. Okay, so in the examples, we need to construct the influence line for the vertical reaction at A of the beam. Okay, so we have a simply supported beam which is 10 meter length. Okay, so the support beam is at A is a pin, at B is a roller. Okay, so as usual, for the first step, so you need to draw the free body diagram. Okay, so you need to apply 1 unit load and indicate the x distance where you measure the distance of the 1 unit load. Okay, so in this case, we measured from the support A. Okay, so and by taking moment about point B, so you will get this particular equation, which is RAY equal to 1 minus 0.1x. And the second step, you can tabulate a certain value by considering a certain intervals of x. So for instance here, the interval is 2.5. So start with x equal to 0 with the interval is 2.5 meter, and the last value is 10 meter. So by using these equations of RAY, so you can get the corresponding value of RAY. Okay, so and you can proceed to plot the graph of ILD, which is specifically for reaction at support A. And actually, you can get the equation of lines, which is equal to 1 minus 1 over 10x. So basically, this is about the line equation, where you have learned this in the mathematics. Okay, so where the y equal to mx plus c. So you can identify the slope, and you can see that the intercept value of c is equal to 1 here. Okay, so let's move to example 2. Okay, so in example 1, the example has demonstrated how we can develop the ILD at support. In example 2, so we will construct the influence line for the shear and moment at the point C of the beam. Okay, so basically you can develop any equation of a shear and moment. In other words, you can develop any ILD diagram for the shear and moment along the beam. So this is an example that we can use as our reference. Okay, so point C is located 2.5 meter from A. Okay, so and the same span of beam used as example 1. Okay, so let's discuss in detail on the solution. Okay, so as usual, you need to develop the equation. Okay, right here, actually, you need to get the equation of at support at A and at B. Okay, but right here, actually, it's not necessarily to develop the ILD for reaction at support. Okay, because our objective in this example is to develop the ILD for shear and moment. So you need to be careful when you want to answer the question in the test or in the final exam. So actually in this problem it's not required to develop this particular ILD as support. So we need to develop the ILD based on the shear and the moment. Okay, so but the first step, you need to get the equation of moment, because to get the equation of reaction at support, because we need to use this particular reaction at support to develop the equation of moment and shear force at point C. Okay, so I hope that you can figure out this. Since this we have seen this in example 1. Okay, so let's focus on the second step, where we can develop the equation of moment and shear force. Okay, so the important thing that you need to know in this particular methods, you need to identify the correct diagram. Okay, so for instance here we want to develop the ILD at the point C. Okay, so we want to know what is the value of a shear force and bending moments when the one unit load applied along the beam. Okay, so so you need to choose whether based on this point C, you can see that we have a left hand side diagram and we have a right hand side diagram. So the left hand side diagram is represented by the AC, meanwhile the right hand side diagram is represented by the CB. Okay, you can choose either one. Okay, let's say we take a look on the first option, which is the left hand side of point C, which is AC. Okay, so this is a left hand side of a point C diagram. So this is a right hand side of point C diagram. Okay, so let's focus on the left hand side diagram. Okay, so this is a based on this diagram. So basically they have a two range, which is 0 to 2.5, which is before point C, and another range is 2.5 to 10, which is indicate that this particular one unit load have been moved beyond the point C. So the first diagram, you can see that the one unit load is available. Okay, and the second diagram, you can see that the same diagram. So actually we didn't make any changing on the diagram. So we just copied down this particular diagram into the second range, but here the one unit load is no longer available. So which means that this one unit load has moved beyond this particular point C. Okay, so where this one unit load cannot be seen in this second range diagram. Okay, so based on this one, based on the first diagram, which is in the range of 0 to 2.5, where what you can see here is a one unit load before a point C. So in this diagram, you can see that we have a RAY, we have a VC, the shear force, and moment MC, and we have a one unit load that measured from support A. Okay, so by using this particular FBD, so you can develop the equation of shear force and the bending moment at a point C. Okay, let's look in detail. Okay, so for the shear force, by considering the summation of force in the vertical, we have RAY in a vertical position. Okay, in the vertical direction, you can see that we have a RAY, and we have a shear force in downward. That's why you can see that the sign is negative, and same position or direction of a one unit load, which is in a downward direction. So and equate all the term with a 0, so to ensure the equilibrium of the system. So you can see that the VC is equal to negative 0.1x. Okay, so let me move on the bending moment equation. So by taking moment about a point C, you can see that we have a 2.5 multiplied with the RAY, so in a clockwise, and we have one unit load. Okay, so the distance of one unit load towards this cut section is equal to 2.5 minus x, so which is this distance. And simplify this equation, you can see that the MC is equal to 0.75x. Okay, so we just obtained two equations, which is shear force and bending moment for the first range. Let's we move to the second range. Okay, so in the second range, we have this particular diagram without the 1 unit load, because this particular 1 unit load has moved beyond the point C. Okay, so based on these diagrams, by considering the summation of force in the vertical, we have RAY minus with VC downwards, and you can see that the VC is equal to 1.1 minus 0.1x. Okay, for the moment, by taking a moment about point C, we have RAY multiplied with 2.5 clockwise. So this gives positive value, and we have internal moment of MC here. Okay, so and no 1 unit load involved in this diagram. So the equation of moments here is equal to 2.5 minus 0.25x. Okay, so okay, what about if you consider the right hand side diagram? Okay, so in the hand, okay, for the first range, which is 0 to 2.5, so you can see that there is no 1 unit load available in this diagram, since this range is 0 to 2.5, which is beyond of a point C. So beyond of a point C, meaning that the 1 unit load is somewhere here. Okay, so that's why when you consider the right hand side of the diagram, for the range 0 to 2.5, so the 1 unit load is unavailable in this diagram. Okay, so meanwhile for the second diagram, which is 2.5 to 10, okay, so 1 unit load is available, since this 1 unit load has moved beyond the point C. Okay, so basically you can use this particular diagram to develop the equation of shear force and the moment. Okay, so I hope that you can figure out the difference between by considering the left hand side and the right hand side diagram. So basically you just need to consider one side of the diagram. Okay, so one side of the diagram in the problem, so it's not necessary to consider both sides. Okay, so basically in the solutions, the ILD diagrams is based on the left hand side of a beam or left hand side of a point C. Okay, so let's see how we can develop the ILD diagram based on these 4 equations. Okay, 2 from the first range, another 2 is from the second range. Okay, so let's look on this diagram. Okay, so basically this is the influence line diagram for shear force at point C. This is an influence diagram for the moment at the point C. So by using the equation of shear force and bending moment that we have developed in this slide, so actually you can simply to plot the ILD for the shear force, but prior to that you need to get the value of VC by using the equation. Okay, so 0 to 2.5, you may use to this particular equation. Okay, so from 2.5 to 10, you may to use this particular equation of shear force, and this is the value of corresponding shear force that you can see in this table. Okay, so by using the value in this table, you can plot the ILD for the shear force. Okay, so same goes for the bending moment diagram. So ILD for the bending moment diagram. So for the range of 0 to 2.5, you need to use this particular equation, 0.75x. Meanwhile, for range 2.5 to 10, okay, so you can use the equations, this particular equation, 2.5 to 0. Minus 0.25x. Okay, so you will get the corresponding value of MC. Okay, so and by using the value in this table, you can simply to plot the diagram, and finally you can get the ILD for the moment at the point C. Okay, so that's it for example 2. Let's we move to example 3. Okay, so in example 3 we have overhanging beam. Okay, so in example 1 and 2 we deal with the simply supported beam. So in examples, we will generate the influence line diagram for the shear and the moment at the point C. Okay, so let's discuss in detail. Okay, so the first step, okay, you need to find out the direction and support. Okay, means that in terms of the equation. Okay, so the first thing that you need to do is you need to draw the free body diagram for the problem. For instance, here you can see that we have RAY, RBY, and one unit load applied, where this one unit load is measured in a distance x from the free end here. Okay, so meaning that this particular one unit is moved from this point towards along the beam towards the point B. Okay, so based on the free body diagram, you can get the direction at support A, which is equal to 1.5 minus 0.25x, and direction at support B. And again, this particular diagram is not necessary to draw, since in the example we need to develop the shear and moment, the ILD for the shear and moment, unless if the question asking to develop the ILD at support. So this particular diagram need to be shown in the answer script. Okay, but here we want to draw the shear and moment ILD at point C. But okay, the first thing that you need to do is you need to draw this particular diagram and find out the direction at support. So the next step, you need to choose, and again you need to choose either you want to consider the left hand side or the right hand side of the point C. Okay, based on the solutions, you can see that the solution considered the left hand side of point C. Okay, so which is from this point to this point. Okay, so based on this free body diagram, you can see that we have a two range, which is 0 to 4, and 4 to 6, which is before and after point C. Okay, let's look on the before point C, okay, which is a range 0 to 4. So and you can see that here we have one unit load available in this range, where the one unit is measured distance x from this free end, and we have a VC and MC, which is internal moment, the internal shear force and the internal moment. And by considering the summation of force in the vertical, you can see that we have RAY, okay, upwards, minus with VC downwards, and minus with one unit load. Okay, so and simplify this, you can see that the VC is equal to 0.5 minus 0.25x. Okay, so for the moment, by taking moment about point C, we have RA1 multiplied by 2 minus with 1 unit load multiplied with this distance. So this distance is 4 minus x. Okay, so simplified the equation. So okay, you can see that the MC is equal to 0.5x minus 1. And for the second range, which is 4 to 6, indicate, okay, this range indicate that the one unit load is move beyond the point C. So that's why you can see that in this particular diagram, there is no one unit load available. Okay. Okay, so by considering the summation of force in vertical, again, you can see that the RAY minus VC is equal to 0, and here you can see that the VC is equal to 1.5 minus 0.25x. Okay, so for the moments, by taking moment about point C, you can see that we have RA1 multiplied by 2, and we have, okay, I think that's it for the moment. So you can see that the equation of moment is equal to MC equal to 3 minus 0.5x. Okay, so we have the complete equation based on the condition where the one unit loads before point C and one unit beyond point C. Okay, and you can proceed to draw the ILD diagram for the shear force and bending moment. And again, by tabulate the value, okay, prior to draw this diagram. So based on this solution, you can see that the interval considered for x is 2 meter. Okay, so we have two intervals, which is 0 to 4 and 4 to 6. Okay, from 0 to 4. So for the shear force diagram, this value can be obtained by using this equation. 4 to 6, you can obtain the value of shear force based on this equation. You can see that for the shear force, okay, so for the shear force, so we have a two value of shear force at point C, which is a negative 0.5 and 0.5. So basically this value of negative 0.5 based on the equations from the first range 0 to 4, which is from this particular equation. Meanwhile, for this particular value of 0.5, this value is obtained based on the second equation, which is the second range, which is based on this 1.5 minus 0.25x. Therefore, the shear force, you need to consider the same point but different equations. Okay, this not for the bending moment. Okay, where because in the bending moment, by using the same different equations and this and consider the same point, so you will get the same value of bending moment. Okay, so this okay for the bending moment, you just using the equations of the first and the second range based on the 0 to 4 and 4 to 6, which is based on this particular diagram. And based on this value, you can plot the shear force diagram and the bending moment diagram. Okay, then you can see it here. Okay, so that's it for the example 3. So we will continue the problem solutions for example 4 in the next session. Okay, thank you.